So good morning, everyone. Victoria Walker. I'm a postdoc at the Hydrology and Remote Sensing Lab in Beltsville, Maryland. I'm here today to give a highlights tour of a very recent paper, less than 2 months old, in Vadozone Journal that is about how long do you have to wait after you install a new sensor before pulling out the old one. So the question for you, you've been observing soil moisture at your site for years. We heard yesterday from a couple of people about the value of long-term in situ records and climatologies. But now you need to replace your sensor models. Maybe they have discontinued your model and you want to update everything all at once. How long do you keep the old ones in the ground once you put those new ones in? You want to do some sort of intercalibration so that you don't have a sharp discontinuity in your long-term record. But that's an open question for us. So to answer that, we look to the Moreno, Oklahoma in situ sensor testbed, or MOIST. And up at the top, there's a link to a paper that has all the information about that testbed. What's on this slide is just specific to this study. So there's 4 sites, A, B, C, and D, that are where their locations are on the map. We've got varying clay contents, with site C being a little more normal for a lot of people at 15 to 25% clay, but sites A, B, and D have a lot more clay. Getting up to site B goes to 50 to 60% clay at its deeper depths. So we're going to look at just 2016 to 2021. And we're going to look at 4 sensor depths, 5, 10, 20, and 50. And for site C, that's actually going to be 40 centimeters, not 50, because during installation, they hit rock and couldn't go any deeper. So in 2010, a whole suite of sensors was established at each of these 4 sites. And I've listed out the ones that are involved in this study here. But then in 2016, they went back nearby, right next to those same sites, and installed a new set of sensors. So we now have our previously established sensors that have been in the ground for years and brand new ones from spring of 2016. And this, if we go through and say, I want all the possible combinations of sensors that are at the same site and the same depth. So at site A at 5 centimeters, what are all the sensor combinations I can make between one old and one new sensor? If we go through and do that for all the sites and depths, we get 154 pairs that then have enough data for validation. And I'll talk a little bit about what that means in a minute. So what do I mean when I say intercalibration? We're talking about a linear calibration. So first thing we do is we take our paired sensor time series and we're subsetting down to whatever our calibration testing period is. And we tested everything from 30 days out to 2 years in monthly increments. And then we fit a basic linear regression to it, where SM new is your newly installed sensor, and that's going to be the orange on these plots, this example plot. And then SM old, or the gray, is our previously established sensor. And then you apply those coefficients to the entirety of the old sensor's time series. And that gives us this intercalibrated version of our previously established sensor. So what we have here is an example of this intercalibration process. And this particular combination is a theta probe and an Aclima TDR 315, I believe. The gray line is our theta. It's quite a bit wetter than our newer sensor. But when we do the intercalibration, it pulls it over so that CDF is more in line. Now you'll note that this is a linear calibration. We're not changing the shape of that CDF. It's just shifting it into place. And so the below panel is a scatter plot example of that, where you can see how the old sensor, before you calibrate it, is much wetter than the newer one. So validation. we needed at least 4 years of overlapping observations. The first 2 years are because we were testing out to 2-year periods. And then I wanted an additional 2 years for validation. But a lot of the pairs have more data than that. We have some pairs that are still ongoing now. And our goal is to standardize that validation while using all of it available. So the approach for that is that for each combination of sensor pair and initial overlap, we take out that first segment for the calibration and then take all the possible 24-month periods after that, aggregate their metrics together, where metrics are bias, RMSE, and Pearson correlation coefficient. And that gives us a synthetic 2-year validation. So that way the validation is always looking at 2 years of our range of soil moisture values. And one of the feedbacks that we got from reviewers is that this is confusing when it's just in words. So we've got some examples here, which is that if you have a sensor pair that has 5 years of overlap beginning in April 2016, if you're doing a 6-month calibration, you'd take out those first 6 months, and then you'd start aggregating over each 24-month period, October 16 to September 18, November 16 to October 18, all the way through until we reach the end of our data, which in this case would be to March 21. And if you were doing a 1-year calibration, you'd do the exact same thing, but you're chopping off the whole first year data for that calibration. So you have fewer of those 24-month periods to aggregate over. So we're going to look at first at the bias of all our pairs. We're defining as bias as new minus the intercalibrated old. So if the bias is negative, that means that the intercalibrated old is wetter, or the new is drier. So on average, across our 4 sites, it takes 6 to 9 months of overlap to minimize the bias. And that's really dependent on what sensor pair you were looking at. There is some improvement out to 1 year, but there was no additional improvement of going out to 2 years. Now, if we look at RMSE, which with the linear intercalibration, we would sure hope that that bias could get to a 0 bias. So that's not unexpected that that's what we get there. We're really more interested in the RMSE of those pairs. The vast majority of improvement in the RMSE is in the first 90 days of overlap. Those small improvements do continue up to a year, but they are very small. And again, there was no additional benefit to going out to 2 years, so I just didn't show it here. You'll notice that site D has a higher RMSE than the other sites. And that's a trend we're going to see through the Pearson correlation as well. And we'll talk about site D in specific at the end. So looking specifically at the 1-year overlap, most of our intercalibrated pairs get to an RMSE of about 0.03. There's only one combination that with a linear intercalibration couldn't intercalibrate well, and that was the combination of the CS616 and the Aqua TDT. And that just means that with this linear intercalibration process, it didn't intercalibrate. Now, there were 9 pairs out of those 154 that failed, so they weren't able to get to an RMSE of below 0.05. 7 of those 9 involved a CS616. And I've listed what those pairs were, although it's not overly important to see what exact pairs those were. It's more that 5 of those 9 were at site D. That's the column on the right. Whereas the other 4 were scattered between the other 3 sites. Now, if we look at Pearson R for those same sets of pairs, and these are just the pairs that occurred at least 5 times in the test bed. There are other pairs that aren't pictured. The Pearson R did not depend on overlap length. What you got after the first 30 days was, for the vast majority of sensor pairs, what you were going to get after 6 months or after a year. And as you might expect, it is heavily dependent on clay content. That as your clay content increases, our intercalibration correlation went down. And this is another point where you notice that there's something a bit wonky about site D. That pair that had the higher RMSE, you can see has a lower Pearson R in this metric, this 616 and the TDT combination. Which is, again, it had a higher RMSE. It didn't linearly correlate as well. But across the board, we get pretty decent correlation coefficients between our sensor pairs. Now, we've been asking ourselves, what's up with site D? Or at least I've been asking myself, what's up with site D? Because it's certainly a little weird. Had a higher RMSE, lower Pearson R. So this is the average of all the pairings at site D. And it's also a time series of the 5 centimeter. So in the time series, you see that the 616s are wetter, are much wetter than the other sensors. But that's not unique to site D. That's something we saw at sites A and B as well. And that is, we are using the factory calibrations here. And these are very high clay soils at sites A, B, and D. Now, site D had fewer pairs, 28, than the others. Sites A and B both had 39, and site C had 48 pairs. 15 of those 28 pairs included the CS616s. And for some reason, those did not linearly intercalibrate well at site D, but they worked just fine at the other sites. So I don't really have an answer for what's up at site D with this. I can tell you numerically, we can point to it and go, oh, site D's performance is worse because the 616s had a hard time intercalibrating at this site. But I cannot say why that is, because they are able to do fine at the other sites. Site D is not the one with the highest clay content, that's site B. And site D's bulk density is not anomalous, it's in line with the other sites. So here we have just a quick plot of bias and RMSE. On the left of our panels are uncalibrated. If you just took 2 overlapping data sources and plotted them against each other, what are their bias and their RMSE? And the right side of the panel is after a year of intercalibration. So you can see that for sites A, B, and D in particular, there's a very large difference between what our sensors are telling us is the soil moisture. Now, if you go to, you might be asking yourself, well, my site doesn't have as much clay as these did. These are all high clay. Do I really need to do this? To which I'd say, look at site C. Site C was better without intercalibration, but it's still certainly not perfect. It doesn't have a non-zero bias, and its RMSE is still above that 0.04 number that the remote sensing people would like to see. However, with intercalibration, we can get that to a near zero bias and get our RMSEs to a nicer level, with the exception of some outliers where there were some pairs that just did not intercalibrate well. So our recommendation, if you know in advance that you're going to be replacing your soil moisture sensors with a different model, plan to collect 6 to 9 months of overlapping data. And if you can, extend that out to a year, because you still did get some improvement out to a year. And there's something reassuring about having a full year of getting a full range of your possible soil moisture values. And that's where I'm going to end it today and ask for questions.
Thank you, Victoria. Oh, we got lots of questions.
Hello. Do you have an idea why those sensors fail to intercalibrate? Differences in technology or something like that?
So Nathan suggested I add sensing volume to that answer. I myself do not have an answer for why certain pairs failed to intercalibrate. I know that 7 of the 9 involved a 616. We were in high clay soils. A linear intercalibration, maybe it didn't need linear, maybe it needed a higher polynomial in order to work. But no, I myself do not have any particular ideas about why those sensors failed.
Okay, so I know.
Okay.
I'm gonna make a big guess. This is terrible, but I'm gonna say this. So just in case you're so I'm Chad. The 616 is like 23 or 24 years old. So it's the only one of all the sensors that actually does not measure conductivity. And I don't know if you know what the conductivity of that soil is, but my guess is that it's probably a little on the high side. And that would cause the problem because since it's not measuring it, there's no way for that factory calibration to correct for it. So it's going to overestimate. And that's a very common problem with the 616. I would, something that's like nearly 25 years old. It's older than a lot of the people that were here. And so I would not have I just recommend nobody use it. Even though it's my sensor, I tell you, I would try to use something else that actually measures conductivity. The only people that I would say that is suitable for the use that keep on using the CS616 are those who do a soil specific calibration and have been using it for a while. And it's still very suitable for that, but for inner comparison, if you're using factory cal, it's going to be challenging. So I think that the data looks very reasonable.
I'll just respond to that a little bit, is that could be the sensor being replaced. So it's useful to still do it in the analysis and say, look, if you have problems, here you are. And we wouldn't deploy a 616 now.
But it is worth noting when it's being replaced, it has high EC. Oh, sorry.
If you're replacing a 616, like they already have them installed. If you've not done a soil specific calibration and you're just basing off the factory, you're going to want to, definitely want to do what you were doing, but recognize that there may not be really good correlation at the high ECs just because the other sensors are going to correct for it when this one did not. And so you're going to have to use something more than probably a different algorithm to compare them together.
When you were installing the new sensors to compare for calibration, how did you situate them within the pit face relative to the old sensors?
So that's probably a better question for Mike or Tyson. But it's a different pit, correct?
So depending on the pair that you're talking about, some of them are in the same pit. They're just, here's the 616s, here's the Teros, the so on and so forth. On the next year, we don't dig up the old pit. We have a new pit, and it's usually within a few meters. Basically making sure we stay within our confine and not out in the pasture. So the ideal, and there's some paperwork out there that says, we have this argument, dig a new pit. Should every sensor be in a new pit? Might be a good option there so that everything is equally different. So we would always recommend now, I recommend different pits. I'd rather not dig up a pit and maybe disturb something that's been working great and then have to do an intercomparison on that one as well. So.
Oh my goodness. So thank you for attacking this important question. My question was, and thanks Chad for setting the stage because he gave me the exact example. If you are replacing because you know from other evidence a newer model to be better, than the model you're replacing. Have you considered correcting the historical record with your calibration? And I'll also just point out the role of heterogeneity in that mismatch, because with pits a few meters apart or even a few inches apart, heterogeneity has scale and it has amplitude.
So yes, that is what we're doing here is we are intercalibrating the historical record. So your new sensor is just whatever the new sensor is measuring, but the old sensor has been adjusted to hopefully better match.